Right. Next, I'd like to move ahead and make a fundamental transition in the semester from kinematics, which is what we've just been looking at, to dynamics. And so previously then, in chapters 1, 2, and 3, we were looking at kinematics. And so that's the study of motion. But without worrying about what causes the motion. Now, what we're doing is we're going to dynamics. In dynamics, we are concerned with what causes the motion. So we're looking at what causes the motion. And so we're looking at things then like forces, etc. So we're going to need to define what those are in order to understand chapter 4, which is where we're going now. So we're going to be looking at Newton's laws of motion, which is kind of the backbone of physics. So if you get anything out of this class, you would certainly want to be able to know what Newton's laws are and be able to apply them. Okay, and so before I get to that, though, let me just talk for a second about Aristotle's laws. And these aren't true, but it's the way that we tend to naturally think. And so that's the reason why I'm going to bring them up here, is that we have to unlearn some of the things that have seemed kind of natural to us. Aristotle's first incorrect law is that you have to keep pushing on things to keep them moving. So implied in this statement is that the natural state for an object is to be at rest. And so I could take, for example, this calculator, and I could move it, and notice that it goes to its natural state, according to Aristotle. It just goes to rest immediately. And so to keep it moving, I've got to keep pushing on it. Okay, and so you could understand, perhaps, why Aristotle would believe that that were a fundamental law. Because everything that he saw, if you didn't keep pushing on it, it would come to rest. And if you were, say, running away from a bear, and you had a cave, and so you needed to pull a rock in front of the opening of the cave so that the bear wouldn't come in and eat you, you would know that you have to keep pushing on the rock in order to get it in front of your cave. And so it's understandable then that as a survival instinct, you would be fooled into thinking that that might be a natural law of the universe. But turns out that that's wrong. That is just not true. As a matter of fact, it's kind of the opposite of this. In Newton's first law, you have to keep pushing on things. You have to, in Newton's law, let me just state this a little more clearly here. The natural, this is true now, the natural state of motion of an object is to move at a straight line at constant speed. unless you're acted on by an external force. Or influence, because we haven't really defined force yet. All right, and so whereas Aristotle said that things will just come to rest and you have to keep pushing on them to keep them moving, Isaac Newton says that the natural motion is to keep moving unless something acts on it to change that motion from constant velocity, which is straight line constant speed, is the same thing as constant velocity. And so we could say, well, the reason that calculator tended to go to rest immediately is because an external force was acting. And that external force was, can you guess? That's right, friction. Friction is the external force that brings it to rest. And so what you would be doing then by pushing on it is you would be balancing out that external force with your own external force. Okay? And so that's how you would be able to maintain the motion. But it's much more complicated and involved than Aristotle's law. And a lot of people still tend to believe it. If you look back at models for whether or not the Earth is in motion as it rotates on its axis and orbits the sun, some of the main arguments for it not being in motion was that if you jump up in the air, why doesn't the Earth leave you behind? Okay, because the Earth is moving, you jump up in the air, then you lose contact with the Earth, and so you should be leaving the Earth behind, and the Earth should go flying out from under you, and you go out through some door and go rolling around in the parking lot 3 blocks away. Okay, and that just isn't observed to happen. And the reason for that is that we're moving right along with the Earth, and just because we lose contact with the surface of the Earth doesn't mean that we come to rest immediately. That if we're thinking in those terms, why doesn't the Earth leave us behind? What you're presuming there, the false presumption, is that your natural motion is to come to rest the second that you lose contact with the Earth. And similarly, I can remember when I was a little kid in an elevator, I was always trying to figure out these disaster scenarios. And so I was wondering what would happen if some practical jokester cut the cable on the elevator, and how could I survive? And so I'd be in free fall, I'd be speeding up, and so I realized in a flash of brilliance at about maybe 4 years old, that if I jump up in the air just as the elevator smashes into the ground, then I'll be able to just open up the door and walk out and I'll be fine. And so even at that age of 4 years old, I had incorporated Aristotle's laws into my belief structure about the laws of the universe. And so it's a natural thing. It's something that we have to unlearn. But just losing contact with the elevator doesn't bring you to a screeching halt. You still keep moving right along with the elevator. And so that's essentially what we're saying then with Newton's first law, is that you tend to just keep moving in a straight line at constant speed forever. And we've already kind of presumed this with our laws of kinematics, haven't we? Because in the x direction, at least, if there's no acceleration, we have constant velocity. So isn't that true? If we have constant velocity and no acceleration, that means that the acceleration is dv dt, the derivative of velocity with respect to time. And so if the velocity is constant, that tells us that the acceleration is equal to 0. Okay? And so that's really another restatement of Newton's first law. That if there's no external forces acting, there's no acceleration, because acceleration is the manifestation of an external force. And so this is stated as a separate law, that is actually a subset of Newton's second law. Newton's second law is the most important relationship in physics, or at least in this semester's physics. F, which is the vector sum of all of the forces that are acting, is equal to ma, where m is our mass. And so mass then is a measure of the inertia of the object. But what is that? What's inertia? Well, inertia is just the tendency of an object to resist changes in its velocity. Okay, so the key word here is resist. Inertia makes the object basically stubborn. It doesn't like changes in its motion. And so an object can have inertia and mass without having weight. And so oftentimes we confuse mass with weight. But mass is not the same thing as weight. Because we can still have mass, which is a measure not only of the inertia in the object, but a measure of the number of particles in an object, which determines its inertia. Examples of these particles would be protons, neutrons, and to a smaller extent, electrons. There are lots of electrons, as many as there are protons, but electrons have very little mass. So that's what I mean by to a smaller extent, the electrons, in terms of a measure of its mass. So let's say that I have something with a fairly modest amount of mass. It would also have weight on the Earth. But mass and weight aren't the same because I can remove something from the Earth's gravity and it still has the mass, even though it's weightless, say floating around in space. And so let's say that I see this pin go floating by as I'm working on the International Space Station. And this thing is bothering me because I'm trying to make a repair. And so I fly swat it out of the way. It's gone. Okay. But and so I go, well, that's because it was weightless. Wrong. It's because it had very little resistance to changes in its velocity. It was easy to fly swat it out of the way because there was very little change in its velocity. But then, armed with that success, next, as I'm working out there on the International Space Station, I see this chair go floating by. And so I go, well, it's weightless too. And so I give it a little kick to try to knock it out of the way. I hit it with my hand, and my boot and my glove explode. Okay? And I break my hand. Okay? Because this has resistance to acceleration, even though it doesn't have any weight. And so you all know what happens if you lose pressure in your suit, right? In space, there's no longer pressure pushing on your body this way, but there's pressure pushing outward, and so you tend to explode. So I explode, and I break my hand, just because I don't know the difference between mass and weight. Okay, and so it's very important then to realize that mass is related to weight on the surface of the Earth because weight is a certain type of force. Okay, but it's not the same thing. They're not equal to each other. And so we talk about something having a certain kilogram weight, mass, and then sometimes that's confused with a certain weight measurement in English units, like a pound. You could say, well, 1 kilogram is 2.2 pounds. And so those kinds of comparisons are misleading because we don't want to get caught up in this thing where we think that mass is the same thing as weight, because it's not. Okay? But in Newton's second law, we also need to define what a force is. So we can go to the upper projector for this. Force is a vector quantity, and basically there are two different kinds of forces. There are direct contact forces, and these require the two objects to come into contact with each other. So this could represent a push or a pull from a chain, or friction on a surface, or air resistance, viscosity, say if you're swimming through water, or you fall into a big vat of honey or something. Or a buoyant force is another type of a direct contact force, or spring force, or just two objects pushing against each other. Those are all direct contact forces. And we can also distinguish those from long-range forces that don't require contact. And so these are things like gravity. You don't have to be in direct contact with something to feel a gravitational force. Electrical and magnetic forces, and also strong and weak nuclear forces are long-range forces as well. And so it might make sense then to think in terms of these forces as being fundamentally different. And in a sense they are. But when we talk about mass, for example, the inertia of an object works in terms of its resistance to changes in velocity, or therefore resistance to acceleration. And so an object then, if it's being slowed down or sped up or moved along a curved path, it's going to resist that. And so inertia then mediates the response of the body to applied force. And the inertia is directly proportional to the mass. Okay, so trying to put that all together then, we can say, well, it makes perfect sense to me that if I push on something, like this calculator holder here, then I'm exerting a force on it, sure. But what about when I release this pin from rest? Then while it's falling, how does it know that the Earth is there? Well, that's because of one of these long-range forces. And it's the main one that we'll be dealing with in this class. That's the force due to gravity. But would you believe that actually the direct contact forces are the ones that are the phony ones? They're not the real ones. The real forces are the forces that act through a distance. Okay? Because, for example, let's say that I sit on this table here. As I sit on the table, I feel the table. I say, well, yes, I'm in direct contact with this table. But that's not true. If we look at the table has a bunch of electrons in it, and then in my body, as I'm sitting on it, I have a bunch of electrons that repel the electrons in the table. So I'm never really touching that table at all. I may think that I'm touching the table. My senses give me information that trick me into thinking that I'm in direct contact with that table, but I'm actually being levitated here by about a 1 angstrom gap, which is about 10 to the minus 10 meters. But nevertheless, I'm not in direct contact with that table. And anytime that you touch something, although you may feel sensors that say, yes, I just touched that object, you are just feeling the repulsion. Let's say there's a tack here, and then that comes close to your finger. Then your finger gets deformed, and the nerves are sending you information then to your brain that tells you you've been touched or you've been stabbed, in the case of where it would actually puncture the skin. But there's actually still that little 1 angstrom gap always there. So, believe it or not, you've never really touched anything in your life. You just think you have. So I usually get a lot of people that want to argue about that. But that's the advantage of doing this on video, so that I don't have anyone to argue with me about it. Okay, so that's the real kind of force then, is the distance force. And the ones that are direct contact are actually illusory. They're not real. They just seem real because our senses tell us that they're real. So how do we represent forces? Well, we can represent a force by a vector. Okay, so that force has a certain magnitude and a certain direction. And so let's say that I wanted to push on this mass with a force, and let's set that force equal to 10 newtons. You know what's a newton? Well, going back to the definition of F equals ma, force is equal to mass times acceleration. And so the mass then would be in kilograms, always measured in kilograms. The acceleration would be in meters per second squared. And so we define then a newton as the, in terms of the units, as kilogram meter per second squared. That the actual definition, that's not a definition, that's just an equivalence in terms of combinations of fundamental units. But to define the newton, we can say that this is the force required to accelerate a 1 kilogram mass at 1 meter per second squared. Okay, so sometimes I could give you test questions that are concept questions, and you will see some concept questions on quizzes that are coming up. But in this case, I could do something like it's the force required to, and then here we could have blank, and then blank. And then this could be move, and that could be 10 meters per second squared. Or we could mess around with the definition. But if we had a 1 kilogram mass here, and we had a 10 Newton force acting on it, and our definition of a Newton is the force required to accelerate a 1 kilogram mass at 1 meter per second squared. What do you suppose the acceleration would be if we had a 10 Newton force acting on a 1 kilogram mass? And here, let's assume that there are no other forces that are resistive forces that are acting, like friction or air resistance or any of those kinds of things. Well, we could go right back to Newton's second law, and here we don't have to worry about a combination or a vector sum of forces yet. We only have one force acting. And so we could write that as 10 newtons equals mass, which is 1 kilogram, times A. And then solve that for A. So A then would be 10 newtons divided by 1 kilogram or that would be 10 meters per second squared. So does that make sense? If our definition for a Newton is the force required to accelerate a 1 kilogram mass at 1 meter per second squared, and then you apply 10 times that force, you should get an acceleration that's 10 times greater. And so that's what we're saying here. Now, did the units of Newton per kilogram add up, or reduce, I should say, to the same thing as meters per second squared? Remember, a Newton per kilogram is a kilogram meter per second squared, mass times acceleration, divided by kilogram. We cancel those out. We see that, in fact, a Newton per kilogram is the same thing as a meter per second squared. And that's always a good thing to check out once or twice, but you don't need to do it every time. And once you know that these units are dimensionally consistent within a problem, you can just assume that the units come out right in the end and not have to go through that kind of a treatment. Okay, so that would be the acceleration on a 1 kilogram mass. But now, let's take that same amount of force and apply to a 10 kilogram object. Now what's the acceleration? Well, now we have 10 newtons equals 10 kilograms times A, or A would be 10 newtons divided by 10 kilograms, which would be equal to 1 meter per second squared. Okay, so 10 times the mass means that we have 10 times less acceleration. So if the force is constant, as the mass goes up, the acceleration goes down. But that should make sense from our definition of mass as being a measure of inertia, because if we are pushing on something that's more stubborn to acceleration, then that means that we're going to have less acceleration, given that the force is a constant. So another way of saying this then is that the mass is inversely proportional to the acceleration if a constant force is applied. Okay. Now, there are many different kinds of forces that can act on different objects. And another kind of force that we haven't looked at yet, but that is worthwhile to look at, is what's called the normal force. Now, by definition, the normal force is always perpendicular to a surface. And usually when we apply the normal force to a discussion like this, at least at first, we do it in terms of a resistance to some other applied force. So here I'll write F normal for the normal force. But if this 10 kilogram mass is sitting on a table, then that means that the normal force has to be pushing against something. Turns out that what it's pushing against is the weight of the object. And so normal force then tends to oppose the weight on a level surface. And the weight force we can write as F gravity is equal to, sometimes we call it W for weight. It's equal to m times the acceleration due to gravity. Okay, so here we have an acceleration that is due to a long distance force, not to a direct contact force, as was the case in the previous two examples, but to a force that's acting through a distance, all the way from the center of the Earth to the object. And so we can say then that the weight of the object, which is just due to the fact that this thing has mass and is being pulled on by the Earth, is equal to mass times the acceleration due to gravity. Okay, so that should make sense. We already know that gravity produces an acceleration. And since F equals ma, then this tells us that if gravity produces an acceleration, then there must be a force associated with that, and that force is the weight force. So here, I'm not going to call it W, just because we use that symbol for work a lot, but rather the force of gravity I'll write as mg, and usually I'll just write it that way every time, so there's no confusion about that. So we might ask then, in the case of this 10 kilogram mass, what is the weight force? Well, F of g then would just be equal to 10 kilograms times 10 meters per second squared, or that would be equal to 100 newtons. So you can see that if we called the weight the number of kilograms, we'd be off by a factor of 10, because we wouldn't be including the acceleration due to gravity, and we would be not using Newton's second law properly. Okay, so for this problem then, I can label mg then as 100 newtons. And you might wonder, well, how many pounds is that? If you have something that is about 100 newtons in magnitude, that might be something like 20 pounds worth of force. There's roughly a factor of 5 difference between pounds and newtons. It's actually, I think, 4.5, but roughly a factor of 5. So it'd be equivalent to about 20 pounds of force for this thing at a 10 kilogram mass. Remember that 1 kilogram is 2.2 pounds. So that is actually 22 pounds. That kind of keeps you in the right ballpark. So with miles per hour, that's something like 1 meter per second is 2 miles per hour, and maybe 20 pounds is like 100 newtons, or 2 pounds is like 10 newtons. Okay. But we'll be using newtons and our general MKS units of meters, kilograms, seconds in the vast majority of the problems we'll be looking at. So if we wanted to figure out what the normal force was in this case, we could say that the sum of the forces acting on this object is equal to 0. And how do we know that? Well, because the mass is sitting on a horizontal surface, and so therefore there's no net force acting on it in the vertical direction. If there's no net force, then it's not moving, because it wasn't moving to begin with. If it's moving and there's no net force acting on it, then it maintains its velocity. But in this case, since it's not moving and the forces add up to 0, then what that tells us is that there's no acceleration. And so then we can write then, using head-to-tail addition, here's the normal force, here's mg, and so they add up to the 0 vector. And so if we define the positive direction to be up, we can write this as F normal minus mg equals 0, or the normal force equals mg. Okay, so this is often the case then if an object is sitting on a level horizontal surface, is that it is experiencing a force which is pushing up from the surface. Now, where does that force actually come from? We could imagine that the atoms in here are connected together by little molecular bonds that are like little spring-like forces. So it's a lot like putting this thing on a little trampoline membrane or something. And then it stretches the springs until the springs push back with an equal force. And they're not really springs, but they act like they were. And so you can imagine that that's what's creating this force, is all of those little spring-like forces that are binding those molecules together, which conspire because they've been displaced. And you can't see the displacement much, but they are being displaced a little, and they push back. And that gives you the equal and opposite force that goes along with what we call the normal force. Then, there's Newton's third law. There's much more to the second law, which I'll talk more about later. That in the third law, basically what we say is that for every action, there's an equal and opposite reaction force. Okay, and so do you see then that that is the case with the situation that we just looked at, with the mass sitting on the surface of the table? There's an action force due to gravity, but then there has to be a reaction force that pushes back, and in that case, that's the normal force. You also have action-reaction forces occurring with rocket propulsion. So I'm going to attempt to make this water rocket shoot off. Actually, I think I better stop there. Well, to be continued.